make ocean-going robots. This is a scale model, not actual size. It's a little rubber robot, but they are normally about sea kayak or surfboard sized with solar panels on the top. And they spend months out at sea collecting scientific and military data on all different kinds of missions. Fisheries protection, anti-submarine warfare, oil and gas exploration, environmental monitoring, fisheries protection, etc. And so it's a little different environment than most of the talks that we've talked about with there's not a lot of cloud involved. Our only connection to the outside world in most cases is Iridium, which is 30 cents a kilobyte, and we're lucky if we can get 60 300-byte messages through an hour. Different scale entirely, but we do have to be extremely reliable. Again, these things are, without a support network, out at sea for months on end. So we've learned some things about writing reliable services. A lot of them are coming from the industrial automation background, which is in part where I've worked in the past. Before coming to Liquid Robotics, I was at Oracle. The last thing I did at Oracle was work on the Java 8 team for streams. But before that, I worked on Java Real-Time and a bunch of the keynote demonstrations that James Gosling had at Java 1 for dancing robots and marble sorting machines and the Audi Stanford autonomous car. And working on those projects is what got me hooked in robotics. So this was and since I also scuba dive and have reef aquariums, a marine robot was kind of a natural fit. What we're building here are durable systems. The idea is that unlike shore-based systems where if something fails you can just shoot that instance in the head and start a new one, you probably have to keep running in this case, even in the presence of failures. And that over time, especially the long periods of time, partial failures are expected, so that you have to actually recover from them. You can't just move on and start over. And I'll start with a brief example of a tragedy that happened in 2008. This is one of the early Java real-time projects, and they were replacing a traditional ladder logic glass manufacturing assembly line. And the problem with ladder logic was if you wanted a second assembly line, you had to essentially European handcraft another one. There was no kind of economy of scale that you wanted 5 lines. Each line was built individually in place for that particular task. So they wanted to update that by about 100 years in technology to move to Java real-time and actually being computerized to begin with as well. So in the first week of deployment, they had a really tragic operational failure. The way the system worked was, under any given point in the line, 170 2-meter by 3-meter sheets of glass passed every minute, okay? And one of the gap sensors on this assembly line didn't adjust properly, and glass started to back up, which resulted in a massive pile of broken glass in the middle of the assembly line, which took them 5 weeks to clean up. And they were about 2 months total before they were able to get the assembly line back on track. And of course, this happened in the first week of deployment, so it was not exactly confidence-inspiring. So what actually broke? Well, in Java real-time, it looks kind of like a normal thread, except for one unusual thing, which is something called wait for next period. So threads in Java real-time aren't like threads in normal applications. You're not trying to process as many transactions per second as possible. Instead, it's more important that the transactions happen exactly the right time. If you had a movie player that showed you the entire movie in 30 seconds because it had great throughput, that wouldn't be particularly valuable. Instead, you'd rather have a movie player that showed you all the frames without jutter, or buffering or any of those other problems. So the main construct of Java real-time is wait for next period is when it's time for me to run again, I'll run again. So here's there's their control loop. And it runs forever. The way that you shut down these plants is you stop injecting glass into the beginning of the system, and when the last one exits, you can then just turn the power off. There's no normal shutdown procedure for the programs. So the way the program works is that it reads a sensor, and then gets the thickness back that's measured from the piece of glass. It adjusts the gap of some piece of handling equipment that maybe accelerates the glass or turns it in a different direction. And then once it's done that, it just goes back to waiting for next period until it's time to do this again. Okay? So what actually broke? In that read sensor method, what it did was it wrote to a serial port a carriage return, and that told the sensor to give me the current value. And then it read a line in from that sensor, parsed the integer that was there, and then returned the result. So back to our previous method, this is the thickness result we got right here, and then it would adjust the gap based on that thickness. However, they had only done partial testing, and the C code, which was actually on the other end of the serial port, had a this printf statement, %4d, for printing out an integer. And these are some sample values that came out of the sensor. And it works great at 1085, 1061, I think these are microns, 1094, and then it hits 978. And there's a space here. Well, parseInt doesn't handle spaces. So it threw a numeric format exception, which was then caught at this catch exception all. They printed a stack trace, which was pretty good, but they then decided that they were going to throw an error, unchecked. And if we look back at their previous method, they're not catching error. So in fact, the entire program shut down, which is why the gap was no longer adjusting anymore. So one bad value kind of killed the whole thing. So after consulting with us at Sun at that time and learning how to use Java a bit more, this is the fixed version of the program that we had, and it has a bit more safety in it. We're no longer catching exception, we're instead catching throwable, so we catch the errors that were there. We now run the wait for next period in the finally clause rather than just as part of the loop, so that even if an exception was thrown, we still call wait for next period and basically continue to run forever, even in the presence of an exception being thrown from this particular method. The problems that I had, as I kind of mentioned, is they had limited experience with Java APIs. They were mechanical engineers coming in this and trying to do control systems in a high-level programming language. They developed their parsing routine from samples coming from the instrument rather than any kind of specification, which is how they missed that space in the numeric number. They didn't really handle the errors properly. They didn't know what to do with a numeric format exception, and since they didn't really expect it, they threw an error, which, again, because they weren't Java programmers, they thought that was a reasonable thing to do. And they hadn't done a lot of unit testing or integration testing of the individual components. They had no idea how to decompose this to test the individual pieces for, for example, they could have mocked out that sensor so that the whole system would have run with in a test environment with all possible input values, including things that are really bad. Even still, okay, so the new version may handle spaces better, but what if the serial line gets corrupted and it just sends line noise? There's still not a particularly good handling for that. What if hitting sending that carriage return doesn't result in a value in a timely fashion? There's still lots of things that could break. So I'm going to talk about some things, recommendations that we've come up with in our style, and they're not necessarily hard rules. Some of them are opinion. The main thing that we're going for is consistency and predictability. So we apply the same behavior across the entire program so that all systems that are integrating with all components that are integrating with each other have a similar behavior. So you don't have a mismatch or impedance mismatch of behaviors between components, and that's a discipline part. That's not a hard rule that says you shall do this and only this. Instead, it's a follow this particular discipline unless you have a justifiable exception, in which case you actually document it. And the other thing to do is avoiding ritual practice of, we've always done it this way, we don't know why, but this is the way we do it. The rules that you have in your discipline should be articulated. So, examples, I'll give a direct example of this, regarding how you throw exceptions. Don't throw bare exceptions like that error that they were throwing. If you're going to throw an exception, throw something meaningful, a subclass of an exception. Occasionally it's okay to throw an illegal argument exception because, well, the argument's illegal, but better is that numeric format exception or something more particular. Just naming the exception may not be particularly valuable. In some cases, if you can provide additional context in the exception so that later diagnosis or better printf or printout of the exception provides more context to resolve the problem, that can be useful. In your code, you're not required to declare on methods that you throw runtime exception or error. You're allowed to do that. You can actually add to your throws declaration, as you'll see on many of the JDK classes, the runtime exceptions that it throws, or on the rare occasions, errors. And in fact, that's how the JCK tests are developed. They fully document the throws and of runtime exceptions that are thrown by this method, and they Java doc them as well. And you may not think that that's a big deal until you are trying to figure out what exceptions might be thrown by this particular method. So for catching exceptions, it's like Pokemon, you should be catching every throwable. Not necessarily immediately, so don't rewrite every catch exception or every catch to catch throwable. That's a bad idea, and you've probably seen recommendations against doing that. But you should be thinking about, if a throwable were thrown at this point or an error, where would it be caught? And there should be an answer to that in every case. Nothing gets out completely. You must have a backstop for every possible error or exception or runtime exception that could possibly be thrown, and an understanding in your mind of where that is going to be caught. So if you don't catch an exception, what happens? In the regular thread, it goes to something called the Uncaught Exception handler, which normally just prints out the exception stack trace and stops the thread. So your thread is dead at this point. If you're, let's say your program is composed of many threads and this thread was doing something critical, well, all those other people who depended on that thread aren't going to get any response, and there's nothing in the system which is going to restart that thread automatically for you. For timer tasks, the same happens, and that's because timer tasks are, in fact, just a thin layer on top of threads with a priority queue that decides when the next task is going to be executed. They also don't continue, except for one weird wart, which is that if something throws an interrupted exception, timer task for some reason will continue when that happens. The really scary part of timer task is that all the other timers which are tasks which are associated with that timer are also dead. So if you use the same timer for multiple tasks, everybody dies at once, and that's pretty bad. And that's one of the reasons that people recommend switching to executor service and scheduled executor service rather than timer task. There are other reasons as well, but the bad behavior of timer task or timer in response to a uncaught exception is one of them. So for future and scheduled future, the possibility that the task may throw an exception is part of the expected behavior. And in fact, when you call get to get the result of the future, it will throw an execution exception wrapping whatever exception was actually thrown by the task. And that none of the other futures using that executor are impacted by the fact that your future through a bad exception. They're completely unaffected. There is still one scary bit in that if your scheduled future, this is something that you've scheduled to execute on a periodic basis, for example, throws an exception, it's never executed again. That's something that if you look at the kind of Stack Overflow metric of how many times has this question been asked, it's actually pretty common that people don't notice that their scheduled future will never be called again if it threw an exception. So another case of uncaught exceptions is, unlike these where you're asking somebody to execute code on your behalf, is that code you execute on other people's behalf. So this would be things like a listener API. So somebody hands you a listener and you call it. Well, that listener could throw an exception, and now it's you that's responsible for handling what happens. Other people's code is definitely worse than yours. So if you agree to take a listener from somebody that you're going to call back when something happens, those callbacks that you are providing will throw exceptions, including errors and other things that are, you should treat it as kind of hostile as possible. And that's where you can think of the backstop, that's now you providing the backstop in calling those. So for example, if you're calling listeners, that you should wrap those calls in a throwable, catch throwable. Log the exception, and definitely register a uncaught exception handler. Other things we mentioned that in a lot of these cases, the service or the thread is now dead. So you may want a watchdog in the system somewhere which was responsible for restarting tasks that die, either scheduled futures or threads as needed. And we'll talk about that in a bit. So here's an example of listener callbacks, and we've got the set of listeners that are registered with our particular service. We call each of them in turn with the event as it occurs, and if they throw anything, we log it out. Things that we still could be doing. Well, we're calling toString on this listener. I kind of omitted that for brevity. Their toString method could still throw, so you would have a throwing exception inside the catch block, which would be bad. You got to kind of be totally paranoid about the things that could possibly happen in these cases. You might have a policy that if listeners throw exceptions, you remove them. Maybe you would maintain a counter of how many times it's failed. Maybe you throw it, you eject them on the first failure. Those policies don't always work because if, for example, you have some kind of intermittent failure where it only fails if the internet is down and then starts working again just magically later, maybe it's best to just ignore the failures as transient. And one problem that you can still have when you're calling back these listeners is that what if this listener goes into an infinite loop? Well, there's no particular strategy for terminating that listener in a reasonable amount of time, and then continuing to execute the other ones. So you may wish to run either all or each of the listeners individually on their own async future, so that they don't have the ability to either block you from processing future events or from interfering with each other. This is a particular annoyance for me. I hate people who write code like this, which is that they took the trouble to create a method, but if you pass it garbage, they just pretend that you never called the method. The question is whether or not this is ignoring a bug or not. And my feeling is that if the behavior is such that you're effectively ignoring a bug, you shouldn't write it like this. The kind of key question of whether or not this is a reasonable or permissible thing to do is whether or not the method is mutative or not. So if this method just did something innocuous like print out the current object to the console, or something that didn't mutate the state of the system, then it may be okay to just ignore this particular method and not do anything. But if this was, set the current access token and you just ignored that, you've left the previous access token in place by ignoring the null, for example, which means you now have the wrong access context for future calls to the service. So there's a lot of cases where you definitely shouldn't use this particular style, because if it's supposed to be iterative, you can get the system to a state that it's not supposed to be or doesn't believe it should be possible to be in. Yeah, and you're propagating more nulls. In this case, I had it, a lot of time these ignore null methods are void methods where they don't return anything, but I made it worse here, where return null. For the next case, which is informal exceptions. So what if you regard null as an exception that hasn't been thrown yet? If you try and do anything with it, it will be an NPE. And you have to treat it the same way that you would treat an exception, and that it requires special handling. You can't use the same handling that you would use if an actual object was returned. So in many ways, null is the informal exception. And it's really quite annoying. It's informal because you still have to deal with it. You can't just ignore the fact that it's there. And if you do choose to ignore that and just proceed merrily along, you're going to get a null pointer exception, at which point your informal exceptions materialized into a real exception. And there's a lot of recommendations, particularly in places like effective Java, to avoid the style of using nulls. For example, if you're supposed to be returning a list of items, some people would return null. The better answer is to return collections.emptyList. For example. And that lets you have symmetric handling with no special casing in the return result. If, in fact, the return result should be exceptional, let's say return the list of registered users. Well, returning an empty list is a reasonable thing to do. If the result you return is one that can't be represented in something like an empty collection, yeah, then it's time to throw in a real exception. Don't just return null in that particular case. So runtime exceptions. So we've got gone from the informal exception to an actual exception. And the main idea of runtime exceptions is that you should be catching them as close to the source as possible. A lot of the runtime exceptions, at least originally as they were designed, are designed to indicate programming errors. And the main thing you want to do is make sure that you don't lose the context for what was going on at the time. So if you had that number format exception from a misparsed integer, if you catch it 50 methods up the stack, it's hard to figure out what was actually going on or what you intended, because you lose all the context of the intermediate stack frames and what variables were local variables were in effect at that time. So it's best to catch runtime exceptions as close as possible. And as I mentioned, rather than just catching runtime exception generically, you should try and catch specific exceptions if possible to provide more appropriate handling for that particular case. For something like numeric format exception, sure, go ahead and catch illegal argument exception rather than the numeric format exception. But if, in a lot of cases, it's best to catch the particular subclass of runtime exception. And as I mentioned, if the method doesn't declare, or in your code as well, if the method you're calling doesn't declare any runtime exceptions, or you don't declare any runtime exceptions in your throw statement, it's effectively unhandled. You should assume that whoever's going to receive this exception probably hasn't taken it into account. And in your own code, the way around this is actually to use your code coverage and unit tests to make sure that you're actually handling runtime exceptions. So you run your unit test, you then look at the code coverage result, and if you see thrown runtime exceptions that aren't code covered, that means that you're probably not handling those runtime exceptions. So you need to generate additional test cases to cause that code to be covered, and now you can verify that in fact you're handling that particular runtime exception. That works for your code, but for arbitrary libraries, particularly ones where you're not bound to a specific version, where you've done exhaustive testing, you know, version 2.1 of some library may now throw a runtime exception you didn't expect. You know, we're back to the kind of backstop analogy of assume that on any given method call, a runtime exception might be thrown. Where is it going to be caught? That should be a consideration, particularly in the case of libraries that you don't have visibility into. The JDK ones are great because they declare everything and they have a very stable interface, so you're not going to get very many surprises. But you know, some random Apache Commons library probably doesn't have that kind of discipline that they may suddenly throw exceptions when they didn't before. Checked exceptions, people are, you know, increasingly enjoying hating on checked exceptions. It was interesting, the founder of the kind of project, the project that I work on at Liquid Robotics was James Gosling. He wrote the first versions of the software and did the architecture. And it was interesting to see his code. There's a Java 1 presentation I did a couple of years ago of what I learned by reading James's code. And his style of handling checked exceptions is a little different than what the normal is. He catches checked exceptions much closer to the source than most people. Checked exceptions rarely ever propagate outside of methods in his code, so they don't have this problem of, oh, now I got to handle that IO exception. The IO exception is never, you don't need to declare throws for it because you handle it immediately. If the checked exception is being thrown out from a method that it wasn't generated in, that's likely because that method was a wrapper method that, you know, just reorganized parameters or something like that. And the place where you're catching checked exceptions, it should be whoever's holding the resource that was involved, whether it's on the stack or in the case of a resource that's held in the field, it's generally a private thread that's responsible for the state of that field. So who's holding the resource and who would be responsible for either retrying the operation involving that resource or trying something different, a different strategy, should be the one who's catching the exception. The ones that are out of left field, because you're not generally catching them, are error and throwable. The first two of stack overflow and out of memory error, these are ones that happen a lot in that case of you calling somebody else's code in the listener or callback kind of situation. They just have a bug in their code where they have infinite recursion, or out of memory error is generally not an out of memory error, but some kind of arithmetic problem where they're suddenly asking for 40 terabytes of space. It's usually, it's far more often an illegal, a nonsensical request than it is an actual out of memory problem. Go ahead, Charlie. Yeah.
I'll repeat it quick. Yes, I'm just thinking about Stack Overflow and out of memory specifically. That usually we get bug reports in JRuby where people are like, "Oh, I rescued stack error, but you know it still was screwed up." And I'm like, "Well, that's because it was a stack error, and it's generally fatal." So, should you handle these things, or should you just assume that this is like a fatal termination of the system?
So we're not allowed to assume that it's fatal, we'll reboot. So we just assume that it'll be kind of self-healing and that it was a bug in the listener, and that we'll just keep trying the listener again. The listener may have damaged its own state, but it probably hasn't had the opportunity to break everything. It's nice that Java locks, for example, are unwound when a Stack Overflow exception is called, not like the early days of C++. Where an exception was thrown and now all of a sudden you've got locks which are in an indeterminate state. That was bad. So it can be better. In a kind of more regular program, I would assume that, or a program where it was all my code and it was some kind of shoreside data manipulation, bulk processing, it would be fine to treat that as fatal exceptions. The next class of error in Throwable is the linkage errors. These are coming from reflection and class loader operations. They're generally from loading dynamic code. Generally, this indicates you've assembled your app incorrectly, in that you've compiled with one version of a library and then shipped a different version of it that has things missing. Exception and initializer can happen without that, and that just indicates that either a bug or some unhandled case is happening in a static initializer for a class. That's one reason why it's kind of suggested not to do anything too fancy in static initializers. Some people do. I've seen things like loading URLs to get icon resources from the internet inside of a static initializer of a class that's being inserted into a hash map that is shared across the whole system. Yeah, there's bad things you can do in a static initializer, but you shouldn't. There's people who actually throw assertion error. This is, go ahead, Ted.
Finish your thought.
There's people who throw assertion error. This is normally generated by the Java assert keyword, which you might consider using for a test environment, or while you're running unit tests, have assertions enabled and include pre and post conditions in some of your code. But in a production environment, you should never have enabled. On the other hand, like I said, we've had code that threw assertion error. That was just extremely rude for a library to do that. Because no one catches it. It was just another error that nobody was catching. And you see occasionally in code where people are calling new throwable. That's generally to capture a stack trace. But there are people who occasionally will throw a throwable too, and that's kind of like the other ones, like error. It's really bad because nobody's catching them. Go ahead, Ted.
So I guess one of the contexts that I'm hearing as a part of the conversation is, in some respects, in many respects, what you're talking about is systems that are deliberately designed to self-heal and recover because we don't have the opportunity to reboot. Right. On the other end of that spectrum, you've got a lot of the cloud players who are basically saying, yeah, when you fail fast, we can just start up a new instance and so forth. How much of your recommendations change in between those two contexts? Or would you consider this to be all applicable advice across any of those contexts?
I guess the applicability becomes a degree of paranoia. You can be too paranoid about that.
Wait, who said that?
What's that?
Who said that? Who said I was too paranoid?
If instances are cheap to bring up and there's already thousands of them all running already, if one suddenly died, it's kind of, who cares? Maybe we'll launch a few more if we need them. This is, yes, as you say, really for the case where you don't have any other alternative. This is, I think, not typical Java code. The place where I had exposure to this, before getting involved in robotics, was things like servlet container, where I was writing the container and Joe Idiot was writing the servlet, and every possible stupid thing that could be done inside of a servlet was done. And I couldn't allow the container to go down just because somebody wrote bad code. It's nice to be in the situation where you can write code that has no impact on the environment that it's running in if it does bad things. I would love to have the luxury of being that free and carefree. So catching summary, informal exceptions, those nulls, you should be handling them in the same method where they were generated, or in the caller of that method, kind of as close as possible. Same handling for runtime exception, and that's not surprising because null is effectively a runtime exception that hasn't been thrown yet. Checked exception, we're handling those in the place that we can retry or do something different, whoever holds the resource. And then all of the other cases, we're relying on wherever we've placed our backstops to handle those exceptions. So, you know, we focused on exceptions so far. There's a lot of problems, of course, which are not exception related. You know, stalls, infinite loops, deadlocks, etc. We'll talk about some of those now. We still use synchronized a lot in our programs, mostly because it's very convenient, but we avoid blocking at almost all costs. So we don't do any blocking on calls to our synchronized methods. If somebody has access to our public API from another part of the program, we don't do any block on the synchronized methods that they're there. If the method is doing something that requires synchronization, it's kind of an immediate operation or one which has an immediate operation and some amortized cost like hash map rehashing, but it doesn't block indefinitely. And on the outbound side, we avoid calling any APIs that might block while we're already holding one of our locks. You know, this might sound like too rigorous a rule, and we have violated it in some places in our code, but it's an example of that kind of discipline rather than you must do this. This is, you know, kind of a style that we do for consistency to avoid problems throughout the code base. You know, the rest of it is kind of not being a jerk. So, for example, never ever synchronize on something you don't own. They may be using that that object for synchronization for some other purpose. It would be, you know, let's say you were going back to Java 4, 1.4 before the Java util concurrent utilities when synchronize was the only operation. And you synchronized on random objects. Well, in a multi-threaded environment, you could easily kill the program because you were holding a lock that was disabled the ability of any other thread to make progress, even though you weren't really that thing. It's kind of odd that you can synchronize on anything, even if you don't conceptually own it. But that's the way it's set up. If you require fine-grained locking, you don't have to lock on your own object. It's pretty common. For example, let's say you have to maintain that list of listeners. I won't recommend that that's the way you should actually do it, but you could have a separate private lock just for modifying that list of listeners on events that wouldn't lock your entire object, but just the sublist. And if you should really only do that finer grained locking if in fact you're experiencing contention. It's good to start off with just using more granular locks and then refining them as you find your contention points. And if you do need to block things like reading from I/O, you should do that on a private thread or an asynchronous future that's separate from your main API. And that comes back to the earlier thing of never blocking on the API thread. Where possible, use the non-blocking concurrent classes and the atomics. The new operations that are available in Java 8, like compute if absent, etc., are a real godsend for this. They make using those concurrent classes a lot better. It was amazing that the number of times I saw, well, I used concurrent hash map. Well, this is still a check then act usage, where they would get something for the hash map, assume that oh, it's not there, well, I better calculate it and then put it back in and then have a collision because there were in fact two threads doing the same thing. The Java 8 additions to concurrent hash map have improved that a lot. We like copy on write array set a lot and list as well if you need ordered. I actually wrote a copy on write navigable array set for Java 8. So we use this not because it's a high performance concurrent collection, mostly for its very desirable iteration property, in that whenever you try and iterate over it with an iterator or in a for loop, it just makes a snapshot. And you're immune from future concurrent modification exceptions. And it's not nearly as heavyweight as the concurrent set, the regular concurrent hash map based set. Discrete lock objects are useful for multiple conditions, and when you need to do speculative locking where you do a try lock, and if it doesn't work, well, then you'll do something else. That's the one real downside of synchronized is that when you call the method, you're agreeing to wait an indefinite amount of time in order to get that lock. And there's no way to say, well, I don't care anymore, or I'm ready to give up, or only do this if it's available. The reentrant lock and read-write lock are the alternative if you want to, only lock if it's available. And for a lot of places, we've moved away from actually using synchronized to using the atomics. This is for things like updaters, counters and things like that. The old patterns from Java 5 days of a synchronized method to update a static synchronized method to get like an instance ID. Now just replace it with atomic long or something like that. Thread pools. We've already talked about these in the context of executor service, but definitely don't write your own. There's now a common pool in Java 8, but should you use it? This is a shared resource. You have the possibility that other people may be misbehaved. We used Jetty 8 as our onboard mini web server, and we were having it share a thread pool with a lot of our system scheduled future tasks. And it turns out that it's really easy to create a denial of service attack with Jetty. Just run curl in a loop. And unfortunately, it's not as NIO as it might be, because it then takes every thread from your pool and attaches it to a servlet operation. So we had to give Jetty its own pool. It will only start queuing when it actually runs out of pool threads. So until it gets execution exception, it'll continue to, or rejected execution exception, it will continue to start new futures, which is really bad and not really friendly to other people sharing that pool. So the thing, you have to be worried about how the other people in that pool sharing it with you are going to be behaving as well. So for our pools, typically, for example, we don't allow, we generally don't allow people to do blocking operations on futures, either scheduled futures or futures. If they want to, they can start their own thread. We let if you know that the operation's short or has a short timeout, like under 20 seconds, then sure, go ahead and block for a little time. But we want most things to complete in under a second or two before returning to the pool, so that other futures can also execute. And that becomes the problem of pool starvation, that all threads are checked out to execute some future. None of them are doing any work because they're blocked, and there are tasks waiting to be executed. That is kind of the worst possible situation to be in. And we mentioned earlier the problems with scheduled futures execution and when it fails. So what you should use threads for? Well, things that run forever. They have an indeterminate life throughout the system. You can use scheduled future for that if you want something to run periodically throughout the rest of the operation. But if you're going to be blocking for long periods of time, holding multiple locks simultaneously, wanting to do odd things with thread priority, you should really consider doing a full thread. And this kind of summarizes it, that the duration of a thread is indefinite. As I mentioned, we try and keep our executor futures under 2 seconds, so they run quickly and then they're done. Executors, we try to avoid blocking because it is a shared resource. If you're doing operations concurrency, executors shouldn't really be doing concurrency operations where they have to do coordinated actions where they might be synchronized or synchronizing on other data structures. And the state of a future that's running in executor should be either, entirely immutable or at the very least private. It's not shared state with the whole system or other threads. It should be doing, a single task or operation that is kind of isolated from everything, everything else in the system. The result may be then shared back with the rest of the system once it's complete, but while it's running, it shouldn't depend or care about what's happening to anybody else. So if you don't, assuming everything goes well, then you're kind of done if you've written your program correctly. But that never really happens. So it's often essential to have something which is monitoring the system state to make sure that everything is continuing to function. And if it isn't, then attempt to repair the system. And because of those problems with potential that you might have resource hogs, that was in fact one of the problems with the Jetty situation we had where it was sharing the executor pool was we had a Linux hardware tickle that we had to hit every 3 minutes. And we weren't hitting it because Jetty was tied up with a out of control curl operation. So the system was in fact rebooting. So we've since moved to having all of our watchdogs on either their own private threads in a few cases, or using a separate executor pool that has one thread, but since they don't do a whole lot of work, that's not a problem. All the watchdogs share that single thread. The main idea of a watchdog is they don't actually do any work. All they're doing is watching for something to happen. And when something bad is observed, they attempt to do the repair asynchronously. In our case, that means actually running it as a future on the main pool. We do assume that that main shared pool, even though we've had problems with it occasionally in the past, we can't be too paranoid and over-provision pools for everything separately so that there's no possibility that it won't be unavailable. Something bad could still happen, that there won't be a thread available, but probably the system is so messed up at that point that it's not possible to recover. And in part, because we have such a small heap, we can't just create, and a single core, we can't just create more threads willy-nilly every time. It's like, I know, I'll create a thread. We've actually had cases where we ran out of threads before we had moved to executor services. So the watchdog is looking for progress. And the definition of progress is going to depend on a particular service. And this is still the same thing as the cloud operations as well. Your heartbeat check is not just whether the service is alive and can respond to a socket, but that it actually has to be making some kind of progress. That its threads haven't died isn't sufficient. So that the function, there should be a function or a way to determine whether progress is being made by this entity. The second goal of the watchdog service is that unless you can, if you can't recover the resources that are held by the dead thing, then the watchdog isn't really helpful. You have to be able to recover the particular resource in order to restart the service. So you should design your services in such a way that you can reclaim the resources from that service so that you can create a new instance that reuses those same resources, whether it's like a file handle or something like that. In our case, that's most often things like serial ports or CAN bus connections, etc. But without the ability to recover the resource, get the serial port back, which is an exclusive resource, we wouldn't be able to effectively restart the service because the dead instance would still have that resource. This is an example that came up when we were just about to ship an application 2 summers ago. And we had a scheduled future that was dying in production due to exactly the type of error we talked about with an infrequent null pointer exception. And we had an alive check, but it was only checking to see whether the scheduled future existed. It looked to see whether or not the service's periodic scheduled future had been created yet. And if it existed, well, that was good enough for it. It didn't see that the scheduled future was marked done, and in fact marked canceled because it had thrown an exception and the schedule executor had killed it. It was impossible for us to update because we had a fleet of vehicles already in the water, 46 vehicles out at sea. Deploying a new version of the software onto them, we probably would have had at least 3 or 4 bricks. So that's just the way it goes. Whenever you try to do something like that, you're going to end up with a couple bricks. But we could install a plugin. We had a small plugin interface. So we were able to get creative and actually look at the services in place via reflection, and we had essentially a second watchdog implemented in this plugin, which just looked for the brokenness condition of the future existed, but it was in fact done. And if it was done, it set the field to null, so that the normal mechanism that was in the system would then, the next time around, recreate the scheduled future and register it with the executor, so that the system would continue to function. But that was an example of, we can't repair the whole thing or distribute a new version of the software, but it was possible to, with some creativity, repair something in place. And get the mission done. So what have we managed to achieve? We've got a couple hundred vehicles. Some of these vehicles are now up to a year out at sea. Between all the vehicles, we've got several 30,000 days at sea, which is a heck of a long time. I forget what I was going to say. I forgot what I was going to say, sorry. So that one longest mission, that single mission was, we took a vehicle down to Pitcairn Island. Pitcairn Island is in the South Pacific, in the middle of absolute nowhere. It's kind of listed as one of the remotest places in the world, and one of the, they get 20 tourists a year. But they have great fishing shoals, and so they wanted to establish a marine protection area, and we put a wave glider out there that listened acoustically for ships coming, and it could identify individual ships by their prop signature. And based on their frequency of appearance, you could guess what port that they were going to, and then interdict them back at that port and say, oh, what do you guys got in your hold? So this mission lasted a year, and the vehicle only rebooted twice during that year. And one of those was in the wintertime when it was very dark. This was actually in our summer in July, and it ran low on battery. So it had, it was a stormy couple of days and didn't get enough charge, and then kind of went into hibernate mode until the sun came back out. But it was out there for a year. When the mission was over, we had the problem of, well, it would cost us $200,000 plus to go back and get it from the South Pacific. That's almost the same cost as the vehicle. Why don't we just sail it across the equator? So it actually sailed from Pitcairn and just kind of chugged all the way into the harbor at Quaihai after 5 months. It turns out that that when you're kind of wave powered, when you try and cross the equator, there's a huge zone there of about 1,000 kilometers at the equator where there's not a lot of wave action. The doldrums. So it was kind of stuck for about 3 months crossing that 1,000 miles. But it was slowly plugging away, and there was good sun, of course, because it's nice days at the equator, but it eventually got home. That's one of our longest missions so far. But as I mentioned, we have offices in Kauai on the Big Island. It's mostly training and maintenance there. If you want to learn how to pilot wave gliders, that's where they send you, or deploy them in the field or service them. But we also do our development testing there, and it's kind of nice to be able to go out and debug on a boat. That was a new first for me a couple of years ago. I won't necessarily recommend trying to code on a boat. Diesel fumes plus closed quarters. I was kind of hanging over the edge quickly. Maybe I need to see the horizon for a while, but it's a lot of fun, and it's kind of interesting that it ends up being very different than the direction that the bulk of the kind of Java industry is heading, but nonetheless still has some lessons for writing services in Java. So, thank you.